So this is the second lecture of the operational amplifier. In this lecture, we are going to talk about the op-amp operation modes. So there are two modes. The first one is the single-ended mode, and the other one is the differential-ended mode. So the first one is either one signal is applied to an input with the other input grounded, or to opposite polarity signal. So this is actually means that in this mode we input one signal only. Okay, so that means that we have one signal, okay, one wave, okay, that we need to input to the op amp, and we do not need the difference between two signals. So that actually means that we are going to apply the signal to one of the inputs and the other one is going to be grounded. So this actually means that there isn't any signal right here. So the signal right here is going to be 0, okay, 0 volt, because it is connected to the ground, and the first pin is going to be the input pin that going to be used. Okay, so that means that we are going to insert, or that we are going to connect the signal to the one input from the two inputs. So that actually means we have said that the the operational amplifier does the difference between the two inputs. Okay, that means that this operational amplifier has two inputs, and the operational amplifier takes the difference of these two inputs and then output the result. But right here we are going to add the signal in the first input, and then in the second input we are going to add 0 volts. So this actually means that the difference between them is going to be the same, this signal. So that means that this signal is the signal that's going to be amplified. But we have learned that we have two inputs. One of them is negative and the other is positive. So in the negative, if we use the negative input, that means that we are going to invert the signal. So the signal is going to be inverted. But if we use the positive terminal right here, okay, that means that the signal is going to stay at it is. So that means that the signal is going to remain the same, okay, but of course is going to be amplified, but the signal, the values, or sorry, the wave is going to stay the same wave, but is going to be amplified. Unlike the first one, if we connected the wave to the negative input, that means that we are going to invert the signal. Okay, so that means that if the signal starts from 0, that means that the signal is going to start from 90. Okay, and if the signal or the signal starts from 90, that means that the signal is going to start from negative 90 degrees. Okay, so this is what the inverting and the non-inverting connection is going to be, and we are going to explain that in more detail in the next slides. We have the second mode. The second mode is the differential ended. So the differential ended, we have explained that two opposite polarity out of phase signals are applied to the inputs. So that means that we have two signals, okay, that we are going to connect one to the first input and the other to the second input. Okay, so that means that the amplifier, the operational amplifier, going to take the difference between them. Okay, and these two signals has two opposite polarity, okay, or we could say that these are out of phase. One signal starts from 0 and the other, for example, starts from 30 degrees or starts from 90 degrees. That is what out of phase means. Okay, and signal are applied to the input. So that means that these signals are going to be applied to the signal, to the inputs. Okay, so that means that we are going to use the two inputs. In the first mode, we use only one input and the other going to be connected to the ground. Okay, we could connect it like this, or we could connect it like this. Okay, the common mode input signal. So in the common mode, two signal voltages of the same phase frequency, okay, and amplitude are applied to both inputs. Let's just read it again. In the common mode, two signal voltages of the same phase, frequency, and amplitude are applied to both inputs. So what's going to happen? That means this common mode is actually means that we have two signals. Okay, these two signals are exactly the same in from uh, they have the same voltage, the same phase, the same frequency, and also the same amplitude. So the common mode means that we are connecting two signals are exactly the same. Okay, one to the first input and the other to the second input. So that actually means that we are connecting two signals identical, one to the first input and the other to the other input. So when equal input signals are applied to both inputs, they tend to cancel, resulting in zero output voltage. We have said that the operational amplifier, actually take the difference between the two signals. If we have this signal right here, okay, and we have also the same signal connected right here, so the difference is going to be taken. So actually this wave going to cancel this wave, and this also the same, and this cycle going to cancel this cycle. So we are going to have an output with zero, okay, with 0 volts. Okay, so that means that these two signals are going to cancel each other because they have the same value. For example, one signal has the value of 5, and 5 minus 5 is going to result to 0. It has the same concept of working. Differential amplifier. The differential amplifier amplifies the difference between its input terminals and rejects their average or the common mode. Again, the differential amplifier, okay, amplifies the difference between its input terminals and rejects their average or the common mode. So this actually means that the differential amplifier, or this amplifier, the amplifier that we are talking about, takes the difference between the two input terminals and rejects their average or the common mode. Okay, so this equation says that we have vid, okay, equals to v1 minus v2, okay, and we have vcm. This is actually mean that this is voltage common mode, okay, and this equals to v1 plus v2. Okay, so the voltage common mode, okay, actually it is their average. We have said that the differential amplifier rejects their average, and their average is the common mode. Okay, so the common mode is the average of the voltage inputs. Okay, so the average of them is going to be the VCM. Okay, and the VID is actually the resulting voltage from the two inputs. Okay, because the amplifier takes the difference between them. Op-amp input signal modes. We have talked about the common mode, so let's see. Common mode rejection means that this unwanted signal will not appear on output and distort the desired signal. So the common mode rejection, this is a mode in the operational amplifier, means that this unwanted signal will not appear on output and distort the desired signal. Okay, the common mode signals, noise, aka the noise, generally are the result of the picked up of radiated energy on the input lines from adjacent lines, the 50 hertz power line, or other sources. So the common mode signals, okay, it is actually signals, okay, that are equally, but these signals aren't ideal equally. Okay, so that means that these two signals, there is going to be some differences, but these differences are very small, so we are going to call it a noise. So the common mode signals, aka the noise, generally are the result of the picked up of radiated energy on the input lines from distant lines, the 50 hertz power line, or other sources. So there is many sources that provide a noise, and we do not want that. So the common mode rejection is the unwanted signal will not going to appear on the output and distort the desired signal. So this is what a common mode rejection is. Desired signals can appear only one input or with opposite polarities on both signals are amplified and appear on the output as previously discussed. So the desired signals are going to appear on the output. As you can see, if we connect the signals in these two modes. So these two modes are the only modes that's going to give us the output that we need, that output that we desire. But this common mode is not going to give us an output. And also, if there is some differences, small differences that are called noises, these noises are going to be cancelled as not going to appear in the output. So this is what this slide talks about. The unwanted signals, okay, aka noise, appearing with the same polarity on both input lines are essentially cancelled by the op amp and do not appear on the output. So unwanted signals, aka the noise, okay, appearing with the same polarity on both input lines are essentially cancelled by the op amp and do not appear on the output. So that means that the unwanted signal are going to be cancelled based on the concept of the common mode rejection. The op amp input signal modes. Okay, we have talked about the common mode, so we are going to continue talking about this mode. So the measure of an amplifier's ability to reject common mode signals is a parameter called CMRR, called common mode rejection ratio. Okay, so the common mode rejection ratio, okay, the common mode rejection ratio is the parameter that we use to cancel the noise that we do not need. Ideally, an op amp provides a very high gain from a differential mode signals and zero gain for common mode signals. So ideally, we have talked that ideally is an op amp that doesn't exist, only on paper. This ideal op amp provides a very high gain for differential mode signals and zero gain for common mode signals. The higher, okay, the output loop gain with respect to common mode gain, the better the performance of the op amp in terms of rejection of common mode signals, the common mode rejection ratio. So the open loop gain with respect to the common mode gain, okay, the better the performance of the operational amplifier in terms of rejection of common mode signals. So this is actually means that the open loop gain, okay, the open loop gain with respect to the common mode gain, okay, so the gain of the open loop, the gain of the input with respect to the common mode gain, okay, or the noise gain, the better the performance of the operational amplifier in terms of rejection of the common mode signals or rejection of the noise. The signal, the common mode it is called the common mode rejection ratio. Okay, so CMRR, actually the common mode rejection ratio, and this is the ratio that we have explained. Okay, it is equals to AOL. That means that this is the gain of the open loop gain divided by the ACM, meaning that this is the gain or the common mode gain. So CMRR equals to, let me just type it in the whiteboard. The CMRR, the common mode rejection ratio, equals to the open loop gain divided by the common mode gain. Okay, so we have the common mode gain, and we have said that the common mode gain appears when we have two signals are exactly the same, but there is some small differences. These differences, for example, if we have a wave with value 4.8, okay, minus 5 point or 5, just 5, okay, this is going to equals to, sorry, if we have a signal with value 5 minus 4 point, for example, 9, okay, so the results going to be 0.1. So this is a very small value, okay. So these two signals, okay, signal 1 and signal 2, okay, are almost the same. So the difference between them is going to be 0.1, and this is a very small value, so this is going to be considered as a noise. So this is what a common mode gain is. So the gain of this noise is the common mode gain. So the CMRR, the common mode ratio, rejection ratio, is equals to the open loop gain. The open loop gain, actually it is the gain from, if we connect one signal and the other signal to the if we connect one input to the signal and the other input. So this is for V1 and this is for V2, okay. So that is what an open loop gain means. So the two modes that we have explained, the single ended and the differential ended modes, these are the in this case the gain of this case called open loop gain, but the common mode gain called uh, called common mode gain, okay. So we have explained these two parameters, the open loop gain or the open loop differential voltage gain, okay. This is appeared when we connect the operational amplifier in two modes, the single ended mode and the differential mode. In the other parameter, the common mode gain is the gain that in which the difference between two exact signals are very small signals, so this is going to be cancelled, okay. And this is going to be caused by the common mode rejection ratio. The op-amp input signal modes. So op-amp input signal modes, okay, that we are explaining right here, the higher the CMRR, the better the performance of the op-amp in terms of the rejection of common mode, okay. So if the ratio, the common mode rejection ratio, the division from the open loop gain divided by the common mode gain, if it is a higher or a high value, that means that this operational amplifier has better performance in terms of the rejection of the noise. A very high value of CMRR means that the open loop gain is high and the common mode gain is low. So the value, if the value, the same thing, okay, if the value, the value of the CMRR is high, that means that the open loop gain is high and the common mode gain is low. So that actually means that this operational amplifier has better performance in terms of rejection of the common mode or rejection of the noise. The CMRR is often expressed in decibels, okay. So the measurement unit is decibels, okay. So CMRR equals to 20 logarithm analog input, open loop gain divided by the common mode gain. So this is another expression if we need to, if we want to measure the CMRR in decibels. We have a first example. The first example, a certain op-amp has open loop differential voltage gain of 100,000 and a common mode gain, or the gain of the common mode gain of 0.2. Determine the CMRR and express it in decibels. So this actually means that we have an operational amplifier has an open loop differential voltage. Okay, so this is connected in differential ended. Okay, so the gain of this operational amplifier is 100,000. Okay, so the open loop gain is 100,000 and the common mode gain is 0.2. So determine the CMRR and expresses in decibels. We know that the CMRR, the common mode rejection ratio, is the division between the open loop gain divided by the common mode gain. So the open mode gain is 100,000 and the common mode gain is 0.2. So the division of that is going to be 500,000. Okay, we need to measure this in decibels, so we are going to express that in decibel by multiplying this value into 20 logarithm. So 20 logarithm 500,000 is going to be 114 decibels. So this is the first example. So in the next lecture, we are going to explain the feedback equation and the stability of the operational amplifier. So that's it in this lecture. Thanks for watching, and I hope to see you in the next one.